This is where we had stopped, where we discussed how the valve responds to variable condensing uh, temperature. So when the condensing temperature increases, the pressure difference across the valve increases, and hence it starts to deliver more mass flow rate, whereas the compressor is only able to draw lesser mass flow rate. This is true for any expansion device and compressor. Okay, so this opposite uh, reaction to the operating pressure ratio is true for any valve or any compressor. It is just that the expansion device which we were discussing in the previous class now has the added provision of changing the area of opening with degree of superheat. And the degree of superheat varies because when you have compressor drawing less mass flow rate, if this is lesser than m dot refrigerant delivered by the OTXV, then the evaporator starts to get flooded and the length of the sensible heat transfer region decreases. Okay, please remember the TXV does not respond to evaporator temperature. It responds to degree of superheat. Your evaporator temperature could be anything. Okay, so there are two effects now. So when your evaporator starts to flood, we have already discussed that your pressures will rise and hence your evaporator temperature will also rise. So earlier it was 12, now it could be 13. So these are some hypothetical numbers which I have given to explain the phenomena. So it could become 13. But what is more important is what is the degree of superheat sensed by the bulb. If it senses lower superheat, okay, so if it senses lower superheat, it means that it automatically means that the evaporator is getting flooded. And the way the valve is devised is that when you have lower amount of superheat, the pressure from the power fluid is less and hence the valve starts to close. So you will move from 10 degrees C superheat. If you move to 7 degrees C superheat, your valve opening area is less. So when it starts to close, then it will automatically reduce the mass flow rate that flows through the valve. And then even if this amount of reduction is not enough, so it will continue to close. So it is not a digital process. Please realize that it is a continuous process. So it will continue to close till you have a new balance point. And if it is so that it, even if it goes to 5.5 degrees C, yet the amount of mass flow rate delivered by the valve is significantly higher than the mass flow rate sucked by the compressor, it means that you have provided a oversized valve. So that is what will happen if you provide an oversized valve. So there is a possibility of it continue to flood the evaporator. Okay, and then what will happen is the valve will close when the degree of superheat goes below 5, and then after some time it will open again and it will close again. So you will not reach the equilibrium within this range of opening. It means that your valve is oversized. So now you realize that simulating the performance of the refrigeration system across the range of operating condition which you expect it to operate is very important in order to appropriately size the system. If you just size your system for your desired temperature, let's say evaporator temperature and one condensing temperature, then your system is going to not perform properly in other operating conditions. Remember that the condensing temperature is not under your control. Your ambient temperature is going to fluctuate significantly. And hence the modeling part or the system simulation is very important during the sizing of any refrigeration system. I had already discussed the advantages of TXV. So since it ensures superheated refrigerant entry to the compressor, so then you are sure that you will not have liquid entry into the compressor. The compressor is safeguarded. Okay, and since you now have the variable opening area of the orifice, now you can operate your system across larger variation in the operating condition. Unlike your capillary tube, where you are always worried that if the condensing temperature goes too high, then there is an issue of evaporator flooding. Okay, or if the condensing temperature goes too low, then there could be starvation of the evaporator. So such issues will be there in capillary device. Hence, it is still common in most of the refrigerators that we use, because your refrigerators, the condenser is still indoor. So your indoor temperature does not vary significantly, or that is what is expected. You do not keep your refrigerators out in your balcony or in your terrace. You keep it in your drawing room or living room or near your kitchen. So there, the indoor temperature definitely is going to vary, but it will not vary as significantly as your outdoor temperatures of an air conditioning device. Yeah, so it tries to at least maintain a balanced condition. So sometimes that's why this expansion device is also called a balanced expansion device. So whenever it senses uh, flooding in the evaporator, it will try to close the valve. Whenever it senses that the evaporator is getting starved, hence the superheat is uh, uh, increasing, then it will try to open the valve more. So it tries to maintain the balanced condition. The disadvantage is mainly the cost. Okay. The second disadvantage, we have not discussed what are the different types of evaporator. We will not have the time to discuss this. So for the time being, just ignore this. So the first disadvantage is only disadvantage that we can discuss is the cost. So your capillary tubes are almost, you can consider them to be free because it's just a tube of small diameter and length. Whereas the thermostatic expansion devices typically will cost you around 2.5 to 3,000 for 1 ton or 1.5 ton systems. Uh, this is the last expansion device, just an introduction to something called as the electronic expansion valve. Again, this is not very common in most of the systems that you will see in your day-to-day life. The reason for this is the cost. So this is an electronic expansion device, as the name suggests. There will be a circuit, an electronic circuit, which will take feedback from multiple sensors. So what is the feedback? Just like in your TXVs or TVs, whatever you want to call it, you have a feedback in terms of degree of superheat. Now, the mechanical design of the TEV ensured that we always get the opening area proportional to the degree of superheat. That was the ingenious design of the valve. Now, if you have to mimic the same thing by an electronic system, first of all, you need a mechanical valve, which will open and close based on some feedback from the electronic circuit. So the most common one is using a needle valve with a stepper motor on the top. So you can provide the signal to this stepper motor to appropriately rotate the stem of this needle valve so that you open or close the orifice. This is like your tap. Just visualize this valve like a tap where you open or close based on your desire of having the water flow rate. So instead of you rotating the head of the tap, you have a motor sitting on top and it will rotate the stem. Okay, now this is the valve portion. Now what is present in the electronic controller is it requires some operational condition feedback. So what would be the feedback? One is a temperature sensor. So you need to monitor the temperature at the exit of the evaporator, and you also need to monitor the evaporator pressure. Okay, so these two would be required. So this is the bare minimum. Now you can program your controller knowing what refrigerant you are using. So let's say you are using R134A, so you know all the properties of the R134A. So based on the pressure transmitter data, you can convert this pressure data into the saturation temperature of R134. So that will give you the evaporator temperature. And this sensor is again sensing the exit temperature from the evaporator. So you now know that the difference between the temperature sensed by this temperature sensor minus the saturation temperature corresponding to this pressure will give you the degree of superheat. So you can write few lines of code in your controller. Please remember that EES will not work. Any of the property database will not work for your controller. So imagine that you have to integrate everything into a Raspberry Pi or some sort of a small circuitry, so a compact one. So you need to write your own functions now. So you write your own functions, everything you have to code in your controller. Based on that, the controller will continuously monitor the superheat and it will give a feedback to the stepper motor to open or close the valve appropriately. So this is what you need to do to mimic the operation of the TEV using an electronic expansion valve. But the beauty of this is the same hardware can be used for any refrigerant. Whereas in case of TEV, you will have to buy the appropriate uh, valve with the appropriate power flow. You cannot reuse the same hardware for some other refrigerant. But over here, you can have a standardized hardware now because everything is now coded into your controller. So these are quite costly and hence they are used only for extremely large systems or any particular system where you have to uh, continuously monitor, log, and where you can justify the use of such electronic sensors. Okay, so normally they'll cost you around 15,000. The basic model with all the sensors, the valve, the electronic controller, everything integrated, around 15,000 or so. So when you go to a larger capacity, only thing that changes is the valve. The electronic controller, the pressure transmitter, and the temperature sensor, they all remain same. So when you go to larger and larger capacities, the price variability, you will see the sensitivity is less because it is only dependent on this valve. Definitely based on the opening area, you will also require the appropriate stepper motor. You have to apply that much amount of force. This this is just a overview, brief overview of the compressors and expansion devices. Uh, Definitely within this short span, we cannot discuss all the small things about the instrumentation. So there are a lot more things which one needs to discuss about the commercial systems. When it goes to commercial systems, large systems like your Nalanda system or systems which are there in your supermarkets, they have a lot more instrumentation. There are ways of maintaining even constant condensing pressures irrespective of the ambient condition. So there are a lot of instruments which are there, but we cannot discuss right. So any questions that you have from the hardware point of view, the refrigeration systems? People who have joined late also can ask in case you have any query. I'll upload this slide after this class. If you have no questions, then I'll start off with the air conditioning part. So again, in the air conditioning part, we'll only briefly discuss about the psychrometric processes only. We'll not have a lot of time to discuss all the hardwares which are used to control the air conditioning systems. Okay, so we'll just look at the psychrometric processes. Anyhow, we will be people who are going to come to the lab class today, so they'll also see one of the air conditioning simulator in operation. Most of the other students have already seen that. So we will just discuss the basics of the air conditioning system and the psychrometric processes involved in that. So any questions in the hardware part of the refrigeration system? Okay. Great. So yeah, so I had already told you the definition of air conditioning. So air conditioning is not just cooling and dehumidification, which we normally connect it to, but it is just the control of air temperature, humidity, velocity, okay, and something called radiant heat energy level. And the definition doesn't stop over here. It also discusses about the removal of particulate matters, microorganisms, any contaminant gases. Now, in most of our domestic or residential usage, we are not going to have contaminant gases. Definitely, we'll have microorganisms and particles to be removed. So that is dealt by those specific filters. If you are using your air conditioning system in a hospital environment, you will have different kinds of filters called HEPA filters, which can trap even smaller particulate matters. You can have special filters to trap the bacteria. Okay. Whereas the other portion, that is control of temperature, humidity, velocity, uh, radiant heat energy levels, again very specific to industrial application. So as far as the temperature, humidity, and velocity goes, that is what your traditional air conditioning systems does. So you can control the temperature. You will have settings in your remote where it says that you can control your temperature from 16 to typically up to 30 degrees C. Humidity level, you do not have control, but you may have some modes called dry mode where it is expected to remove more moisture content from the air. So you may not have a specific setting in your remote which says that I want to maintain 30% humidity or 50% humidity of that sort, but you will have some modes called dry mode or eco mode or just cooling mode. There are some modes which manufacturers will specify. So all it does is it tries to control the humidity aspect more than the temperature. So when you run your AC in your dry mode, you will see that it can actually overcool the air in order to maintain the air dry. Okay, so that is the limitation of using just a refrigeration system for air conditioning purpose. These things will be apparent when we discuss about the psychrometric processes. And of course, the velocity of air is controlled by the fan. Okay, so these systems are also called as HVAC systems, and the engineers who work in this field are called HVAC engineers. So it's a short form for heating, ventilation, and air conditioning system. But in true sense, the air conditioning definition encompasses all these three aspects. Okay, so you need to maintain the appropriate amount of oxygen level in your air. For that, you require ventilation. You need to maintain particular temperature. It could require cooling. It may require heating also. Okay, and this term air conditioning, because we are always introduced to an air conditioner which only provides cooling and dehumidification. So that's why for layman, this air conditioning is given, this name has been given to only be associated with that process. Heating has been separated out and ventilation has been separated out. But in true sense, all these things are part of air conditioning. Okay, so we have already, I think, discussed in the introduction that Willis Carrier uh, was the pioneer who was working mainly in the psychrometric formula. Okay, he was trying to devise a formula through which we can actually relate the temperature and humidity by some mathematical functions without which we could not have developed the air conditioners that we see today. People knew that if you cool down air, you will be able to condense water. But how much it has to be, what should be the temperature of the cooling coil so that I can remove X amount of water vapor from air. So what is the connection between temperature and the amount of moisture that you are able to remove? That formulation was not present during those days. Okay, and then based on his uh, paper that he presented in ASM in 1911, he got some consultancy projects, and finally he developed the first modern air conditioner in 1915, and it was for an industrial application. It was for a printing company. They were not able to get the desired print quality on paper, and the reason for that was the uncontrolled moisture level inside their uh, factory. Okay, so it was for a printing and lithography company. And then once he successfully made this machine, he got many more contracts from variety of industries as well as for the the commercial spaces. Okay, so be it theaters, be it the shopping complexes in US, okay, food processing industry. He even started getting contracts from the defense companies also. Okay. So air conditioning has very wide range of application. So some of them are listed over here. So any manufacturing industry, be it textile, ammunition, semiconductor, ship, car, power production, any food processing industry will require air conditioning processes. Then the entire cold chain. Okay, the cold chain means uh, the source of where you produce the food, you store in a cold environment, then you transport again to a truck or a vehicle which is able to maintain a constant temperature and the desired humidity. And then again at the location of consumption, also you require cold storage. So this entire end-to-end service, well, nowadays we are getting few companies who are providing this end-to-end services for our agro produce. But maybe a decade ago, we did not have many such companies. So this cold chain is becoming very necessary nowadays because of food security is a big issue. We cannot waste any amount of food given the amount of population that we have and the amount of production that we can have based on the available land. Okay, then these are the new areas where air conditioning systems are finding a huge demand. That is the data centers and servers. And of course, these were always there, all cinema halls, office classrooms, and residential buildings. Okay, so if you look at the Indian scenario, in India, we are getting huge demand in the residential segment and the cold chain because these are the immediate demands. Whereas when you look at China and other manufacturing hubs, their demands are mainly in the semiconductor or manufacturing industries in general. Okay, and of course, these data centers and servers, they are very specific to the locations where they are built. So if you look at the atmospheric air contains, what is the composition of atmospheric air? Does anyone know? Which is the most prominent gas?
Nitrogen.
Nitrogen. Then
Oxygen.
okay. Then third gas.
Uh, Carbon dioxide.
Carbon dioxide. Any
Argon.
other? Yes, argon. So these are the three most prominent gas, but when we look at the percentage of nitrogen and oxygen, the fraction of argon is that insignificant. In fact, the amount of water vapor also would be insignificant in comparison to the amount of nitrogen and oxygen that is present in air. But still, when we look at air conditioning processes, we have to look at water vapor content. Can you tell me why? Rest of the gases, we will treat it as ideal gas, except water vapor. Why do we do that? So the reason is as simple. The other gases which you have mentioned right now, they will not condense in most of the air conditioning processes that we'll discuss. Okay, unless and until you go to cryogenic temperatures, we'll not see the separation of nitrogen and oxygen and argon from air. The composition in air will remain as it is uh, till you go to temperatures low enough to condense the individual gases. Okay, so that's how we produce the medical grade oxygen or the liquid nitrogen that we use in many industrial processes, is to separate out the air into its constituent gases by condensing those gases. But if you don't go to such temperatures, you will have all those gases remaining as non-condensing, whereas this water vapor will condense. So that's why we treat the atmospheric air as non-condensing plus condensing gas. So in non-condensing gas, you have all your nitrogen, oxygen, argon, carbon dioxide, everything. And your condensing vapor is water vapor. Okay, the amount of water vapor is typically few grams per kg of air. Yet we have to treat it separately. We also have pollutants, but in this course, we'll only discuss about the thermal aspects and we'll not discuss about the pollutant filtration and all. So that aspect will not be a part of the air conditioning processes that we will discuss. So from now onwards, whenever we discuss about air, inherently you will have to assume that it is moist air. Okay, so it is dry air plus water vapor. And your dry air is treated as ideal gas. Okay, in fact, water vapor can also be treated as ideal gas only for the vapor part, of course. But when it starts to go to higher temperatures, so if, I don't know if you remember the pure fluids discussion that many faculties would have done in thermodynamic courses, that where you can treat the superheated vapor as ideal vapor and where you cannot treat. So there, so if you look at your PV chart, this is your vapor dome. Okay. Or you can also look at PT chart. Normally at very low pressures, even very close to the dome, you can start treating the vapor. The saturated vapor can also be treated as ideal gas. Okay, so if this is the typical region where you can treat the gases as ideal gases. Okay, but when you go to higher pressures, you will have to go to much higher temperatures for it to be treated as ideal gas. In this region, you cannot treat even the superheated gases cannot be treated as ideal gases. Definitely, you cannot treat anything over here as ideal gas. That is anyhow subcooled liquid. Okay, so the initial formulation of the psychrometric charts assumed water vapor also as ideal gas, and they were not very far away from the actual scenario because the amount of water vapor present in air is very less, hence the partial pressures are very low. So you will see that you will be operating somewhere here. It is just that the condensing processes cannot be mimicked by any ideal gas model, but the vapor present in the air can be treated as almost ideal gas because the partial pressures are low. Typically, this region you have 1% error between real gas and ideal gas. Okay, and for water vapor, the pressures of the order of 10 kPa or below, you can treat them more or less as ideal gases. Of course, in this region. So the initial formulation assumed the dry air as ideal gas and water vapor is also ideal gas. But later on, when we have more and more accurate models coming up, people started incorporating them in the psychrometry chart. And now we don't even rely on charts when we have EES, so we can just directly write codes to get our desired result. The next slide. So the most important property which many of us are confused and find it difficult to understand is the moisture content. So how to treat and how to evaluate the amount of moisture present in the air. What is meant by relative humidity? What is meant by the absolute humidity? Okay, so and many people have a doubt regarding what is evaporation and how is it different from boiling. Okay, so let's target that as a part of our discussion today. So consider that you have a container, no air present inside this container, no leakages, nothing. Okay, just a pipe connecting it to a vacuum pump which has drawn out all the air. Now this contains liquid water. So what would be above this liquid water surface? What is this? This will be water vapor. All the air has been drawn out. Let's assume that the temperature of water is 30 degrees. What would be the pressure exerted by this vapor at thermodynamic equilibrium? Can anyone tell me? Liquid water is at 30 degrees. There is no air inside the system. Can anyone tell me what would be the pressure exerted by this water vapor? The pressure exerted by this water vapor would be equal to P saturation at T equals to 30 degree for water. I think that will be close to 4 kPa. That would be at equilibrium. By equilibrium, I mean the rate of evaporation and the rate of condensation would be same. And hence, if you were to measure the liquid column at any given instant, you will always find that the liquid column is at a particular height. So whatever the initial height was, it will remain at that height. So there won't be any addition of liquid or there won't be any reduction of amount of liquid. Okay, so that will happen only at this pressure. So when the entire system is at equilibrium, the water vapor temperature will be at 30, same as liquid water. Okay, and the pressure exerted by this vapor will be equal to the saturation pressure at 30 degrees. Now suppose by some means, by using this vacuum pump, I am able to reduce the pressure from 4 kPa, which is corresponding to the saturation temperature at 30 pressure at 30 degree. I reduce it to 3 kPa. What will happen?
More water will evaporate.
Water will evaporate. So there will be phase change. Does everyone agree? Whoever is attending the class. If I reduce the pressure above the liquid column now from 4 kPa to 3 kPa, there will be phase change. I will see that the liquid water is evaporating and your liquid column height will start to reduce. Does everyone agree with this?
Yes, sir.
Now, what will happen if by some means, now let's assume that I have another pipe through which I can push steam. Okay, some hypothetical device which is generating steam. There is no air still now. So in this steam, there is no air. It just pushes 100% steam. And I increase the vapor pressure from 4 kPa to 5 kPa. Whatever amount of steam has to be provided to raise the pressure from 4 kPa to 5 kPa, I will supply it through this steam generator. Now what will happen inside this box?
Condensation.
Condensation. So you see that if you move away from this equilibrium pressure, either one of these phenomena will start to happen. If you reduce the water vapor pressure over this column of liquid water, you will have evaporation. If you increase the partial pressure, if you increase the pressure of water vapor, you will have condensation. So the system will back to your 4 kP unless the temperature also starts to change. Okay. Now, will this phenomena change if I introduce a non-condensable gas? So that's why the term non-condensable is very important. So it will not condense during this entire process. So I introduce some nitrogen into this container. Now, how much nitrogen? Let's say I introduce, I don't know, the number of moles of nitrogen required to increase the pressure from 4 kPa to 100 kPa. So I introduce some n moles of nitrogen so that the total pressure above this liquid water now is 100 kPa. The same container. So 4 kPa pressure of water vapor and 96 kPa is the partial pressure of nitrogen. 4 kPa water vapor and 96 kPa nitrogen. Now, if I use this vacuum pump and I draw out the mixture of gases, so some amount of water vapor will be sucked out or drawn out, and some amount of nitrogen will also be drawn out. So don't you think that you will still have evaporation just like in the first example where I had reduced the partial pressure from, rather the total pressure was itself 4 kPa then. So 4 kPa to 3 kPa you had evaporation. So now even if I use a vacuum pump now, you have some non-condensable gas nitrogen. But what you need to focus on is just the partial pressure of water vapor. So if this partial pressure of water vapor goes below 4 kPa by even the smallest of amount, you will have phase change. Can you visualize this part? Okay. So if you have a container which has air inside it and you have liquid water inside it, you connect it to a vacuum pump, you continue to draw vapor from that container, you will see that the water does not boil vigorously in the initial period. Okay, when you reach a particular low pressure, then only you start to see lot of vapor bubbles coming out from the entire liquid column. So that vigorous phenomena will happen only when the pressure above it reduced to a certain value. Till then, you will not see. You will just see that the entire system is steady and air is being continuously drawn out by the vacuum pump. Okay, so let us understand that what exactly happens in the initial period and what happens when you attain a certain low pressure. See, the equilibrium pressure of water vapor is 4 kPa. Now, even if you introduce any amount of or any composition of other gases into this container, the equilibrium partial pressure of water vapor is going to be still 4 kPa as long as the liquid water is at 30 degree and the entire system is maintained at this temperature. Okay, if you have a temperature in equilibrium between the water vapor on top and the liquid water here, then it becomes complicated. For the time being, assume that this entire box is an isothermal box. So even if you introduce nitrogen, hydrogen, helium, any other non-condensable into this and raise the total pressure of this of the gases above the liquid water, the partial pressure of water vapor is still going to be 4 kPa at equilibrium. If the partial pressure of water vapor goes above 4 kPa, you will have condensation and it will try to go back to 4 kPa. If you reduce the partial pressure of water vapor below 4 kPa, it will have evaporation. Okay, so now what is evaporation? See, in evaporation, what happens is just assume that there's a very thin layer of gas just above the liquid water. Over here, you will have pressure of 4 kPa. This is the partial pressure of water vapor, assuming that the liquid water is at 30 degrees. Now, if by some means I draw this vapor out and reduce the pressure over here, then the liquid molecules just at this surface will move into vapor phase and try to replenish this vapor layer in order to regain that equilibrium. Okay, so it will happen just at this surface, at this liquid vapor interface. Okay. Whereas in boiling, what you see is you start to see vapor bubbles even at the bottom surfaces. All the while, when evaporation is happening, you will see that there is no vapor generation in the bulk fluid. But when boiling happens, you will see that the vapor bubbles start to nucleate. The technical word is nucleate from all over the bottom part or the side portions. So everywhere you will see vigorous vapor generation. Now, when will that happen? Can anyone guess or can anyone tell me their opinion? During the evaporation, it is just the process happening at this liquid vapor interface. If you try to remove or suck out vapor from this interface, reduce the partial pressure of water vapor here, the liquid right next to this interface will move from liquid replenish that vapor layer. But when will you start to see vapor bubbles coming from beneath the well below the liquid vapor interface? So that is when boiling will start to happen. Any idea? So boiling will happen when your total pressure becomes equal to the saturation pressure at whatever temperature this liquid is. Then you will see that the phase change occurs throughout the bulk of this liquid. So right now, if your total pressure is 4 kPa, in case you do not have any non-condensable, okay, it is just pure water vapor above the liquid water. Okay, any slight reduction in vapor pressure will lead to vigorous boiling in the liquid column. So that's why when your container is open, let's say in your day-to-day life, you have a vessel which has liquid water. What is the total pressure on this liquid column? It is 1 bar, 100 kPa. Okay, what is the saturation pressure corresponding to the temperature of the water inside your vessel? That would be hardly 4 or 5 kPa. Okay, so the either you raise the temperature of the water so that you have total pressure equals to your P saturation at that higher temperature. That is what we do to boil water. We raise the temperature of the water, or you have to reduce the pressure on top to see the boiling happen. Okay. But in all other cases, you will have evaporation continuously happening because this partial pressure, this 4 kPa is maintained because of continuous evaporation and condensation at the liquid vapor interface, right at that top surface. Yes, if you were to measure if you have a gadget which just measures the partial pressure of water vapor, so you will see that it will be equal to 4 kPa, and how it is maintained, there is continuous some molecules which are going into the vapor phase and some molecules are coming from vapor phase into the liquid. So that is continuously happening throughout that level in order to maintain that equilibrium. So at equilibrium, the liquid to vapor transition and vapor to liquid transition are equal. But you will not see vapor starting from the bottom of this liquid column and traveling upwards. Because for this vapor bubble to be generated over here, okay, at this location, unless and until the pressure inside this vapor is equal to the pressure exerted on top of it, it will not be able to escape up. So even if there is a vapor, just hypothetically, if there was a vapor pocket generated at the bottom, it will still be at this pressure, P saturation at that particular temperature, and it will not survive the 1 bar pressure being exerted. It will not be able to travel upwards. But what is happening at this interface is just specific to this. At this interface, where liquid and vapor is, opposite, vapor and liquid is present, you have the liquid molecules continuously transitioning into vapor and some vapor transitioning into this liquid. Now, if you reduce the pressure suddenly at the top, then you will have either, so if you reduce the pressure, you will push the liquid to vapor process more rapidly. If you increase the pressure of vapor on top, you will start the reverse process. It is somewhat like your chemical equilibrium and ionic equilibrium process. So when you have equilibrium, you have A going into B and B forming A. That becomes the rate at which A is forming into B and B forming back into A, they are equal. Now, if you change any condition, either you will increase the rate of forward reaction or the backward reaction, something of that sort. So liquid to vapor, vapor to liquid transition. So when we try to create boiling at our home, we try to elevate the temperature in order to have, or in order to overcome this total pressure. Okay, so that's why you will see people say that evaporation occurs at all temperature, whereas boiling doesn't occur. Okay, but so if I ask you when does phase change occur, phase change is occurring continuously. If you have any vessel which is containing, so if you, even if it's a closed system, if you have liquid water and some gas on top, you will still have water vapor in that particular gas, and the partial pressure of water vapor will be equal to the saturation pressure at the liquid water temperature. And that's why, again, I'm telling you that non-condensable is very important. It means that there is no liquid molecule of air in this liquid water. Okay, things become even more complicated when you have two condensables which can mix. Then it becomes even more complicated to analyze. Any questions? Okay. So we'll meet again tomorrow. So if this thing is clear, I hope then the definitions of relative humidity, absolute humidity, and everything would be quite easy to understand, and the psychrometric processes will be quite straightforward from now onwards. If you have any questions, you can ask them now.
Excuse me, sir.
Yeah.
Sir, does increasing humidity mean increasing load on air conditioning system?
Increasing humidity means increasing load on the system. Yes, exactly. Because since increasing load, again, your AC, it is dehumidifying as well as cooling. So if you have, let's say, an iron box inside your home, or you're cooking where your air conditioning system is present, you will have humidity rising up. Now that amount of moisture has to be now removed from the air by your air conditioning system. So how can it remove? By condensing that vapor. Now, in order to condense X amount of water vapor, you require to extract X into HFG of water vapor. If you have 1 kg of water vapor going from vapor to liquid, you require 2500 kilojoules of energy to be extracted. That energy has to be now extracted by the AC. Any other question?
So can you please go to your first slide of air conditioning? Sir, here in third line, sorry, in second line, radiant heat energy level. What does it mean to regulate radiant heat energy level?
Okay, imagine that you have to cool the air where you have steel making going on. You are standing next to a blast furnace, or you are standing under a tinned roof. Okay, so then it is not just cooling the air, sensible cooling of the air, you also have to block the radiations. So your tin roof will become warm and it will start to radiate inward into your room. So these are very specific, either in industry or in warehouses you will see. So we do not see radiant heat energy levels significantly so much because we use such building materials in our day-to-day life. We have false ceilings which provide additional insulation and all. We have very thick walls. Consider that you are inside a container, metal container. So reducing the radiant energy level is also a part of air conditioning system. So refrigeration system is just a subset of air conditioning process. So we use it as a tool. Suppose I ask you to increase the temperature of air, you will use a heater. So heater is also another device which is used for air conditioning. If I ask you to increase the humidity inside a room, you will use a steam generator. So that is another device which can be used for air conditioning. I ask you to increase the velocity of air, you use a fan. That is also a part of air conditioning process. So all these devices are part of air conditioning. But we normally associate air conditioners to only refrigeration systems. That is not correct. Anything else? Good that you asked. I missed that part. Okay, so we'll meet again tomorrow. And anyway, I'll meet few of you in today's lab class.